In tonight's Space Dreams documentary, the moon's quiet face becomes a scientific record. A single ancient collision scatters molten rock into orbit. A glowing ring cools into a companion. Chemistry locks in the clues. Craters keep time. Tides slowly widen the distance between two worlds. Settle in for a calm journey through giant impact evidence lunar chemistry and the long echoes that shape Earth. If this kind of deep, peaceful space storytelling helps the mind slow down, please like the video and subscribe to Space Dreams documentary. New cosmic documentaries arrive regularly, and each one is made to drift gently into the night. A bright scar of light circles a young Earth, then fades into a quieter ring. The moon begins as debris from a giant impact, and the evidence hides in chemistry and motion. In that region, molten rock does not fall like rain. It stretches into a rotating sheet, thin at the edges and thick near the equator. The glow is uneven. Brighter lanes mark hotter streams. Darker knots mark cooler clumps that start to hold together. A faint gradient runs through the disk. Heat is strongest near the planet. Cold gathers farther out. The first payoff arrives early. A collision does not only break a world, it can also build a companion when gravity sorts the fragments. Droplets of melt spin outward. Some collide and shatter again. Some merge and grow. The disk looks like a wide halo, not a solid ring. It is a cloud of liquid beads and vapor. The beads trace curved paths that rarely intersect. Their motion is fast, but the pattern is slow. The disk has an inner edge where tides tear clumps apart. It has an outer region where clumps survive long enough to meet again. The boundary is not sharp. It is a zone where stability changes with distance. About 4.5 billion years pass between that moment and the quiet sky today. That span is like counting every heartbeat of a long night, then realizing the night lasts for ages. The number stays round because the story does not need finer marks. The disk cools in stages. At first, vapor dominates. Then liquid droplets become more common. Then solids appear. A grain of mineral forms. It is tiny, but it carries a preference. It accepts some atoms easily and refuses others. The second payoff follows. The moon's later chemistry begins inside a brief interval of condensation. Elements that evaporate easily drift with the hot flow. Elements that stay solid settle into droplets sooner. The sorting is gentle. It is a bias repeated many times. The ring dims from white to orange, then orange to deep red. The outer disk turns from a bright fog into a darker band with scattered molten beads. 2 to 3 concepts hold the scene together. One is angular momentum, meaning spin stored in orbit and rotation. A smooth spin keeps the disk spread out. A weak spin lets it fall back. The second is isotope, meaning atoms of one element with different mass. These masses change how easily atoms slip into vapor. The third is a magma ocean, a global layer of molten rock. Each term stays light. Angular momentum looks like a stretched ribbon that resists being wound up. Isotopes act like similar pebbles with slightly different weight in the same current. A magma ocean resembles lava with drifting plates of darker skin. Each matters because the moon keeps traces of all three. The disk keeps angular momentum in its shape. Lunar rocks keep isotopes in their ratios. Earth keeps the magma ocean in its mixed mantle. The disk does not become the moon in a single step, it becomes many bodies first. At the outer edge, small clumps form then collide. Some impacts are gentle, some are violent. The clumps break and reassemble. Over time, the average size grows. A chain of moonlets circles in the same plane. Each moonlet is irregular. Shadows stretch across their surfaces because they are not smooth spheres yet. Some tumble, some settle into a steady turn. The next payoff arrives. A single large moon is not required at first. A swarm can merge into one body, and the swarm helps explain why the final moon lacks many easy-to-vaporize materials. Repeated heating during mergers thins those ingredients. The loss is quiet. It is a slow narrowing of a particular set of components. A shoreline after a storm offers a comparison. Waves toss shells and stones together. Heavy pieces tend to stay near the break. Lighter pieces travel farther along the beach. Nothing decides. Repetition does the sorting. The disk behaves in a similar way. Gravity is the slope. Rotation is the wave pattern. Fragments are the shells. Over many orbits, the distribution shifts. Some material falls back to Earth. It crosses the inner boundary and is stretched apart. It becomes heat and vapor again. Some material remains outside that boundary. It survives long enough to gather. The scale shifts here. A bead the size of a pebble becomes a moonlet the size of a small world. Minutes of orbit become months of merging. The disk is a thin lens of rock around a sphere. A limit of intuition arrives softly. The exact path from disk to moon cannot be watched directly. The earliest record is erased by later melting and impacts. Models track countless fragments, but resolution is finite. Small collisions blur together. Heat loss depends on grain size, and grain size is uncertain. Even isotope patterns can be overprinted by later mixing. In that region, certainty has a boundary. Beyond it, only ranges make sense. Still, the ranges line up in a consistent direction. A high-energy impact explains a disk rich in Earth-like material. A hot disk explains a moon low in volatile elements. A merging swarm explains the moon's final orbit and spin. One chemistry clue stands out as a steady anchor. Earth and Moon share remarkably close oxygen isotope patterns. The fact is simple. A captured body would likely look different. A co-formed moon would still need an explanation for lost volatiles. The giant impact ties these together. It allows mixing at high temperature. It allows loss from a hot disk. It leaves a moon built mostly from material that once belonged to Earth's outer layers. The disk is now darker. Solid grains glitter like frost in a thin fog. The largest moonlet gathers a faint halo of debris. Smaller bodies trail behind. Their collisions become fewer. The system relaxes. Heat radiates away. The glow becomes a dim ember line around a black sky. As the ring clears, the planet below remains luminous. A magma ocean covers much of the surface. It cools from the top. Dark plates form and sink. Lighter melts rise. The mantle mixes. This payoff arrives without fanfare. The moon's birth is also a resetting of Earth's interior. A single day of impact heat echoes into millions of years of cooling. A single ring of debris becomes a companion that continues to shape tides. The next section moves from the ring's glow to the physics that lets debris stay in orbit instead of falling home. The new ring looks stable from far away, yet every orbit tests whether it can remain a ring at all. The debris stays aloft because rotation balances gravity long enough for clumps to grow. At this distance, the disk has a clear inner border, where tides stretch material into long filaments. It has a calmer outer band where fragments keep their shape. The inner border is not a wall. It is a region where the pull changes across each clump. One side feels a stronger tug than the other. That difference pulls the clump into an oval, then into a thread. The main idea sits quietly. Orbit is not a circle drawn in space. It is a continual fall that keeps missing the surface. The disk becomes a lesson in balance. Gravity pulls inward. Angular momentum keeps material from dropping straight down. A pale glow still lingers in the hottest lanes. The glow has a soft gradient. It brightens near Earth, where vapor stays common. It darkens outward where droplets cool into grains. The first small payoff arrives. A disk can exist only when spin is high enough to keep material spread out. Too little spin and the ring collapses. Too much and the ring thins and flares outward. A gentle analogy holds this balance. A wet skirt spun slowly hangs heavy. Spun faster, it lifts and spreads into a smooth circle. Spun too fast, it flutters and tears at the edge. The disk behaves similarly, but the fabric is melt and vapor. The spin is stored in countless paths. The edge is defined by stability, not by cloth. A slow scene settles in. A single clump drifts near the inner border. Its shadow elongates across the disk. The clump begins round, then a long waist forms, then two lobes appear. The lobes separate into two smaller bodies that drift apart. The motion is silent. The shape change is the story. This leads to the second payoff. The inner border prevents easy growth. It acts like a grinder that turns clumps back into spray. Growth shifts outward where the grinder weakens. One number is enough to hold the scale. The inner border lies at roughly 3 Earth radii from the centre, like placing a small marble 3 arm lengths from a larger ball. The comparison stays simple, because the geometry matters more than the exact value. Inside that distance, tides win often. Outside it, self-gravity begins to win more often. A new term enters lightly. Roche limit means the distance where tides can tear a body apart. The definition stays short. The image follows. A clump is like soft clay held near a strong magnet. The near side pulls harder than the far side. The clay stretches and splits. It matters because it sets a natural gate in the disk. It decides where moonlets can survive. The disk also carries viscosity, a measure of flow resistance. Viscosity matters because it controls how the disk spreads and cools. A low resistance flow spreads quickly and thins. A high resistance flow keeps thicker lanes and stronger gradients. The third payoff arrives. Viscosity helps explain why the disk does not vanish at once. It lingers long enough for repeated collisions to build bigger bodies. The visual anchor changes pace. A broad spiral pattern appears in the disk. Dense lanes curve like a slow pinwheel. Between lanes, a thinner fog shows a darker shade. The pinwheel is not painted, it is a density wave. Matter bunches, then relaxes as it orbits. The wave moves through the disk while the material moves through the wave. This separates two kinds of motion without naming it. The wave is a travelling pattern. The droplets are travellers. The next payoff follows. Density waves can transport angular momentum. They can move spin outward while letting mass drift inward. That quiet transport shapes the final mass of the moon. It also feeds Earth with returning debris. A calm scale shift arrives. A droplet the size of a seed follows a path that lasts hours. A lane in the disk persists for weeks. The cooling of the largest moonlets takes centuries. The settling of the final orbit takes millions of years. The time ladder rises without urgency. Each rung is a slower change. A limit of observation sits in the middle of this ladder. The early disk cannot be sampled directly. The history is reconstructed from later rocks and simulations. Simulations must choose a fragment size. They must choose how heat radiates from vapor and droplets. Those choices shape the outcome. The resolution cannot follow every grain. The smallest collisions become an averaged haze. The limit is specific. The disk's fine-grained turbulence is not fully resolved. It is inferred through simplified rules. Even so, the larger patterns remain robust. A tidal boundary exists. A wave-like spiral can arise. Angular momentum must be redistributed. The section returns to concrete detail. The disk's inner edge shows sharp shear. Material closer in moves faster. Material farther out moves slower. That shear stretches clumps into arcs. It also grinds edges smooth. The outer band shows gentler shear. Clumps can rotate as they orbit. Their shadows stay compact. Their surfaces cool into darker crust with bright cracks. The crust fractures as the interior stays warm. The fracture lines form polygon-like seams. The seams glow briefly, then dim. A final payoff settles without a label. The moon forms where the disk allows survival, not where the disk is brightest. The birth site is set by a boundary in tidal stress. The growth rate is set by repeated mergers and calmer lanes. The result is not a perfect circle. It is a path shaped by gradients. The closing turns soft. The next section moves from orbital balance to the heat inside both worlds, and how molten rock behaves like an ocean. Heat does not vanish after the impact. It lingers as a moving surface that behaves like an ocean of rock. A magma ocean forms because the upper Earth melts deeply, and that melt reshapes chemistry by mixing and sorting. In that region, the surface is not uniform. A thin skin cools and darkens. It fractures into broad plates with sharp edges. Between plates, glowing seams appear where hotter melt rises. The seams drift and narrow. They fade as crust thickens. The first small payoff settles quickly. A molten Earth explains why early material becomes well mixed, so the moon's building blocks can share familiar chemistry. The ocean is not a calm pool. It is a convecting layer. Convection means heat-driven circulation in a fluid. Warm material rises, cooler material sinks. The definition stays short. The image follows. Rising plumes look like slow columns in a lava lamp. Sinking slabs look like darker curtains sliding downward. It matters because circulation erases local differences. It turns patchy ingredients into a more uniform blend. A steady visual anchor forms. A broad night-side arc shows a dim red sheen. A dayside arc is brighter where fresh melt is exposed. The boundary between them is a soft gradient. The gradient drifts as rotation turns the globe. Light behaves as a shallow glow scattered by hot vapor near the surface. The glow weakens where the crust thickens. The second payoff arrives. A cooling skin acts like a lid. It slows heat loss. It extends the time during which mixing continues underneath. One number carries the scale without strain. The molten layer can be hundreds of kilometers deep, like stacking many mountain heights into a single vertical column. The comparison stays simple. Depth means volume. Volume means long cooling time. A gentle scale shift follows. A bubble rises in seconds. A circulation loop turns in days. The ocean cools over thousands to millions of years. The ladder of time stays quiet. Each step is a slower change, not a louder one. Chemistry begins to separate while the flow continues. Dense droplets rich in metal sink. Lighter silicate melt stays higher. Some minerals crystallize early. They form grains that either sink or float depending on density. The physical detail is clear. A boundary forms between a slushy upper layer and a hotter liquid below. The boundary is not flat. It undulates like a slow wave. Where crystals gather, the mixture becomes thicker. Where crystals melt, the mixture thins. The third payoff arrives. Early separation helps explain why Earth ends with a metal core and a silicate mantle, while the Moon is comparatively poor in metal. The Moon inherits more of the mantle-like material because the disk draws from outer layers. A unique analogy holds the idea. A pot of thick soup cools on the stove. A skin forms on top. Stirring beneath still moves the warm liquid. Heavy bits settle to the bottom. Lighter foam gathers near the surface. The soup is not rock, yet the pattern guides intuition. Mixing can be strong and separation can still happen. The pot cools faster at the rim. The magma ocean cools faster at the surface. The next visual anchor arrives in a slow close view. A field of floating crust plates presses together. Their edges grind and overlap. A thin line of melt wells up at the contact. It spreads into a narrow ribbon. The ribbon solidifies into a lighter band. Darker plates surround it. The surface becomes a mosaic. The mosaic shifts as plates break and merge. The payoff follows. The surface texture is not decoration. It controls how heat escapes. Cracks and seams act as vents. Thick plates act as insulation. The cooling rate becomes uneven. Uneven cooling affects which minerals crystallize first. That affects what elements remain in the melt. A calm limit of observation enters. The earliest magma ocean leaves no direct surface to examine. Later impacts churn and remelt the crust. The record is indirect. It is inferred from mantle composition and from lunar samples that carry related signatures. Models simulate convection, yet they must assume viscosity at extreme temperatures. Viscosity at those conditions is uncertain. Small changes in assumed flow resistance can change how long the ocean persists. The limit is specific. The fine structure of early convection cannot be resolved from surviving evidence. Only broad constraints remain. Even so, those constraints point toward a long-lived molten phase. The disk and the ocean interact through vapor. Above the magma ocean, a temporary atmosphere of rock vapor can form. It is thin compared to later atmospheres. It is dense enough to scatter heat and slow cooling. The physical detail appears as a hazy layer that glows more near the equator. The glow fades toward the poles. The gradient follows the pattern of heat and rotation. The payoff arrives softly. A vapor blanket delays cooling. Delayed cooling allows more mixing. More mixing pushes Earth and Moon towards similar isotopic signatures. Similar signatures become a quiet fingerprint of shared origin. The section eases outward again. A molten Earth cools. The disk cools. The Moon gathers and cools. The same physics links small crystals to planetary layers. The next section moves from heat and mixing to the chemical clues that remain inside isotopes and volatile loss. Two bodies can look like strangers in the sky, yet their atoms can quietly match like twins. Earth and Moon share key isotope patterns, and that sameness points back to mixing in a hot aftermath. In that region, the evidence is not a photograph. It is a ratio hidden in minerals. A grain holds oxygen and silicon in a crystal lattice. The lattice has orderly sites. Some sites accept heavier isotopes slightly less easily during evaporation. The effect is small. It accumulates through many cycles of heating and cooling. The first payoff arrives early. Similar isotopes mean the Moon forms from material that is not foreign. It forms from the same reservoir as Earth's outer rock. A slow visual anchor settles in. A thin cloud of rock vapor hangs above the disk like a faint fog. The fog is denser near the planet. It thins outward into a clear edge. Light behaves as a soft scatter through that vapor. The glow is brighter near the inner lanes. Farther out, darker gaps open between denser streams. Within the fog, droplets drift and cool. They condense minerals on their surfaces. They lose some atoms back to vapor. They regain others. This gentle cycling is not dramatic. It is steady. It is enough to push compositions toward a shared average. The next payoff follows. A vapor-rich environment allows exchange between Earth material and disk material, so isotopes can converge even after a violent origin. One key term enters lightly. Fractionation means isotopes separate during evaporation or condensation. The definition stays short. The image follows. It resembles steam rising from warm tea. The steam carries more of the light molecules. The cup retains more of the heavy ones. It matters because hot disks can fractionate volatile elements. They can leave a signature of loss. The Moon shows that kind of loss in materials that evaporate easily. Potassium and sodium are less abundant than simple expectations. The loss is not absolute. It is a shift in balance. The second payoff arrives. Volatile depletion fits a hot disk. It fits repeated melting during moonlet mergers. It fits a long cooling path that favors escape of light components. One number carries scale without clutter. The disk's hottest phase can last for a few hundred years, like a long winter that never reaches true cold. The comparison stays simple. Hundreds of years is long for vapor exchange. It is brief compared with planetary history. This sets a quiet scale shift. Seconds define how fast an atom can hop between vapor and liquid. Hours define how droplets drift through lanes. Years define how long the fog persists. Millions of years define how the final moon cools and locks minerals in place. The chemistry story continues with another term. Volatile means an element that evaporates easily. The definition stays short. The image follows. It is like fragrance leaving warm bread. It fills the air first. It fades from the loaf over time. It matters because the moon is drier and more depleted in volatiles than Earth's mantle. The disk's heat and low pressure encourage that loss. The physical details make the loss tangible. A boundary layer forms above molten surfaces. The layer is thin. It is where evaporation and condensation trade atoms. Above it, vapor streams move outward. The flow creates a gradient in composition. Inner regions are richer in vapor. Outer regions are richer in droplets and grains. The gradient is not stable in place. It slides as the disk spreads and cools. A third payoff arrives. Gradients can produce slight differences between early formed grains and later formed grains. Those differences become a timestamp. They hint at when a mineral condenses and how long it re-equilibrates. A new visual anchor arrives to keep the rhythm. A moonlet surface cools under a thin vapor haze. The surface crust turns grey. Beneath it, faint red glow persists along fractures. The fractures form branching networks. The branches taper into fine lines. The glow retreats inward as heat leaks away. Tiny crystals in the crust record the last moments of high-temperature exchange. After cooling, the record becomes hard to rewrite. The limit of observation arrives with a gentle boundary. Isotope measurements rely on surviving samples. Those samples represent a small region and a narrow set of rock types. Mixing in the mantle can blur earlier differences. Later impacts can melt and reset minerals. Models of vapor exchange must assume how quickly atoms swap across the boundary layer. That swap rate is uncertain. The limit is specific. The microphysics of exchange at extreme temperature is not directly constrained. Only the final signatures remain. Even with that limit, the broad pattern persists. Earth and Moon are unusually similar in oxygen isotopes compared with many simple capture scenarios. The Moon is also depleted in some volatiles. The combination narrows the range of plausible origins. It favors a hot mixed disk formed from Earth-like material. The section draws back to a calm perspective. Chemistry behaves like a quiet ledger. Each entry is small, the sum is strong. Similar isotopes speak of shared source. Volatile loss speaks of heat and escape. Together they frame the giant impact as both mixer and sorter. The next section moves from these chemical fingerprints to the Moon's earliest layers, where floating minerals build a bright crust and a darker interior. A young moon cools from a glowing sphere into a layered body with a bright skin. The first crust forms because light minerals float on a lunar magma ocean and lock in place as cooling slows. In that region, the surface is not yet solid ground. It is a shifting lid of crystals and melt. Bright grains gather at the top. Darker melt remains beneath. A boundary appears between a frothy upper layer and a denser interior. The boundary is wavy. It rises where hot plumes push upward. It sinks where cooler material drains downward. The first small payoff arrives. The Moon's highlands begin as flotation, not as later paint. Light minerals rise because density rules are simple even in extreme heat. A single visual anchor settles in slow motion. A pale raft of crystals spreads across a red ocean. The raft is uneven. Its edges are scalloped like torn paper. Gaps open where hotter melt wells up. The gaps glow brighter for a moment. Then new crystals knit across them. Light behaves as a soft reflection off pale grains. Shadows fall shallow across gentle ridges. The scene stays quiet. It repeats many times. Each repetition thickens the floating layer. One key term enters softly. An orthosite means a rock made mostly of light feldspar. The definition stays short. The image follows. It resembles cream rising and setting on cooling soup. The soup is still liquid below. The cream layer becomes firmer above. It matters because an orthosite matches the moon's bright crust. It explains why the oldest highlands are pale. It also explains why the crust is enriched in certain elements that prefer the melt. A second key term enters as needed. Differentiation means a body separates into layers by density. The definition stays short. The image follows. It is like sand settling in a jar while lighter particles remain suspended. It matters because the moon becomes stratified early. That stratification shapes later volcanism and impacts. The next payoff arrives. A layered moon stores heat differently. A thick crust insulates the interior. Insulation keeps melt pockets alive longer. This delay helps set the stage for later dark plains. One number holds the scale. The early lunar crust can grow to about 50 kilometers thick, like stacking several long city commutes into a single vertical wall. The comparison stays simple and calm. 50 kilometers is not a detail to memorize. It is a sign that the shell becomes substantial. A gentle scale shift follows. A crystal forms in seconds. A raft spreads in days. The crust thickens over tens of thousands to millions of years. The moon's surface then faces billions of years of impacts. The time ladder rises without urgency. Each rung is wider and quieter. A new visual anchor arrives to keep the rhythm. Beneath the pale crust, a darker melt layer circulates. Slow plumes rise like dim columns. Where a plume reaches the underside of the crust bows upward. The bow forms a dome. The dome casts a longer shadow at low sun angles. The shadow edge is soft because the surface is still warm and slightly plastic. The payoff follows. Doming and sagging create thickness variations. Thickness variations guide where later magma can find weak points. Even a small difference in shell thickness can redirect rising melt. The physical details remain grounded. Cracks form where the crust cools and contracts. The cracks are not straight. They branch and curve. Their edges are sharp in shadow. Their floors can glow faintly when heat remains. A thin layer of fractured rubble builds on top. It scatters light. The scattering makes slopes look brighter at certain angles and darker at others. This is not decoration. It is a texture that records cooling. A calm limit of observation appears. The earliest crust is not preserved as a complete shell. Later impacts excavate melt and mix the upper layers. Samples represent small regions. They may be biased toward unusual terrains. Models of crystallization must assume how fast crystals form and settle. Those rates depend on viscosity and cooling. Viscosity at lunar magma ocean conditions is uncertain. The limit is specific. The fine timing of crust formation cannot be pinned to a single value. Only a range is supported. Yet the broad outcome remains consistent. A flotation crust is expected. A differentiated interior is expected. The moon's low metal content is expected when the source material is mantle-rich. The section turns outward again. A cooling moon is not alone. It orbits Earth while both bodies still radiate heat. Tides flex the moon slightly. Flexing adds warmth deep inside. Warmth delays full freezing. The payoff arrives quietly. Even weak tidal heating can help keep the interior active longer. The interior then has time to reorganize. Dense materials sink further. Lighter materials rise. The moon becomes more stable in layers. A final visual anchor slows the scene. The bright crust now covers most of the sphere. Its surface is lightly wrinkled. Long ridges arc across it. Between ridges, shallow basins begin to form. The basins are not yet the dark plains of later times. They are low places where crust is thinner. The shadows there are deeper and longer. The section eases into a gentle transition. The next section moves from layered structure to the marks left by later impacts, and how those marks reveal the early bombardment history. A crater is a quiet bowl, yet it forms in a blink compared with the age of stone. The moon's scars become a clock because older surfaces collect more impacts over time. At this distance, the surface is a mosaic of bright highlands and darker patches. The highlands carry dense fields of small circular pits. The pits overlap. Their rims cast thin shadows that sharpen at low sun angles. Between rims, fine dust smooths the texture. The dust forms a shallow blanket with a soft gradient from ridge to floor. The first small payoff arrives early. Counting craters does not give exact dates. It gives a relative order. More craters usually means older ground. Fewer craters usually means younger resurfacing. The logic is simple, yet the details are careful. A single impact begins with a fast approach. The impactor crosses the last distance silently. Then a shock wave spreads through rock. Material excavates outward and upward. A ring-like rim rises. A central mound can rebound in large craters. Around the rim, an ejector blanket spreads as a rough apron. The apron is thicker near the rim. It thins outward into scattered rays. The rays are brighter where fresh material is exposed. The second payoff arrives. The pattern of rim rays and blanket reveals how deep the impact digs and what layer it reaches. Impacts become probes that turn the moon inside out in brief flashes. A unique analogy holds the idea. The surface behaves like a notebook page left under falling sand. Each grain makes a mark. Some marks smudge older lines. Over time, the page becomes darker with overlapping dots. A fresh page is clear, an old page is crowded. The moon is that page and craters are the dots. The analogy stays gentle. It keeps the story grounded without needing names. A slow visual anchor settles in. A broad basin spans the horizon. Its rim is low and broken in places. Inside, the floor is smoother than the surrounding highlands. A few larger craters sit on the floor like shallow bowls in wet clay. Their rims are crisp. Their shadows are clean. Light behaves as a soft sweep across the basin. It brightens one wall. It leaves the opposite wall in a long gradient of grey. The view holds still long enough to notice layering. Near the rim, the ejector shows faint ridges like frozen waves. Farther out, the ridges fade into a rough pebbled surface. The next payoff arrives. A smoother floor often means later lava or melt fill. A rough ridged apron often means older ejector, preserved. These textures separate episodes without any words carved into stone. One number anchors scale. A large basin can reach about 1,000 kilometers across, like spanning the width of a long continent. The comparison stays simple. 1,000 kilometers is vast on a small world. It sets the sense of size without turning into a list. The scale shift follows. An impact forms the basin in seconds and minutes. Cooling of impact melt takes years. The cratered surface then sits for billions of years while tiny impacts continue. Time expands without strain. A brief event leaves a feature that outlasts oceans and skies. A second visual anchor arrives to keep the rhythm. Bright rays stretch outward from a younger crater. They look like thin chalk lines on dark dust. The rays are not flat paint. They are streaks of fresh fragments. Each fragment is angular. Each casts a tiny shadow at low angles. The rays cross older pits. Where they cross, brightness returns. The payoff follows. Rays are fragile. They fade as micrometeorites churn the surface into darker dust. A crater with sharp rays is likely young compared with one without rays. This offers a simple relative tool. It adds another hand to the clock. 2 or 3 concepts hold the section. One is crater saturation, when new craters erase old ones so counts stop increasing. The term stays light. Saturation means the page is so crowded that new dots replace old dots. It matters because the oldest terrains reach a limit where counting small craters no longer separates ages well. Another concept is impact melt. Melt forms when shock heats rock above melting point. It ponds in low places. It freezes with a smooth skin. It matters because smooth melt can mimic lava flows. Distinguishing them requires careful texture reading. A calm limit of observation arrives. Crater counting relies on assumptions about impact rate through time. The rate may change. It may spike during heavy bombardment. It may calm later. The smallest craters are hard to see at low resolution. Dust can hide them. Secondary craters complicate counts. Secondary craters form when ejector lands and makes smaller pits. They are not independent timers. The limit is specific. Resolution and interpretation set a floor on what counts can reliably measure. Even with these limits, the broad story remains. The highlands are older than the smooth dark plains. Large basins mark early intense episodes. Younger craters mark later quieter eras. The physical evidence stays visible in rim sharpness, ray brightness and overlapping order. The section eases toward consequence. Impacts do not only scar, they also deliver heat and open paths for later lava. They churn the crust and expose deeper layers in crater walls. The next section moves from scars as a clock to scars as chemistry windows, where excavated material hints at what lies below the crust. A crater wall is a cross-section cut into the moon, and it reveals hidden layers in silence. Impacts expose deep material, so scars become windows into crust mantle, and later, volcanic fills. At this distance, the rim of a large crater shows terraces. Each terrace is a step where rock slumps downward. The steps cast alternating bands of light and shadow. Between steps, fresh blocks lie at angles. Their edges are sharp. Their faces show subtle color differences where different layers appear. The first small payoff arrives early. A single crater can sample more depth than a plane surface ever shows. The crater's central peak is the key. A rebound lifts deeper rock upward. The uplift is not gentle. It is fast during formation. It then freezes into a stable mound. The mound stands like a knot in the floor. Around it melt pools and cools into smooth patches. Those smooth patches reflect light more evenly than rough ejecta. This sets a clear contrast. Rough means fragmented. Smooth means melted and refrozen. The next payoff follows. The presence of melt sheets helps separate an impact event from later lava flooding. Melt sheets cling to crater floors and walls. Lava floods can extend far beyond the crater. A unique analogy anchors the idea. The moon's crust behaves like a layered cake that has been struck once with a heavy spoon. The blow cuts a bowl. The cut lifts deeper layers into the center. Crumbs scatter outward. The cake is not consumed. It remains as a pattern. The analogy stays calm. It guides attention to layers without adding drama. A slow visual anchor settles in. The central peak rises from a grey floor. Its slopes are lighter on one side and darker on the other. Fine debris gathers in gullies. The gullies form thin lines running downhill. Near the peak, a bright band marks a different rock type. Farther down, a darker band appears. The boundary between bands is curved. It follows the slope like a contour line. Light behaves as a grazing sweep. It makes the band boundary stand out. The first small payoff arrives again in a new form. Layering seen in peaks and walls constrains crust thickness. If an orthosite dominates shallow exposures, the crust is still present. If darker mantle-like rock appears, the excavation reaches deeper. One number anchors scale. A large complex crater can be about 100 kilometers wide, like the span of a long morning drive across open countryside. The comparison stays simple. 100 kilometers is enough to build terraces and central peaks. It is also enough to excavate many kilometers of depth. The scale shift is gentle. The crater forms in minutes. The terraces slump over hours. The peak cools over years. The exposed layers then sit under micrometeorite gardening for billions of years. The time ladder stretches from a blink to deep history. 2 or 3 concepts hold the section. One is excavation depth, the approximate depth from which material is launched. It depends on crater size and impact energy. The term stays light. It matters because it links surface samples to interior layers. Another is ejecta blanket, the spread of thrown debris around the crater. The definition stays short. The image follows. It resembles a fan of flour thrown onto a table. It lands thick near the hand. It thins outward into specks. It matters because ejecta can carry deep material far from the crater. It can seed distant plains with a thin layer of foreign fragments. A second visual anchor arrives to keep the rhythm. A ray streak crosses older terrain. Along the ray, small secondary craters dot the surface. They align like beads on a string. The beads are not random. They come from chunks that re-impact. Their rims are low. Their floors are shallow. The payoff follows. Secondary craters can mislead crater counts. They can also map the direction and energy of ejecta. Their alignment points back to the source. Their presence shows how far blocks travel. The chemistry thread returns softly. Exposed rocks can differ in composition. Some are rich in calcium and aluminum consistent with bright crust. Some are richer in iron and magnesium consistent with deeper material. These differences are modest. They still matter. They provide constraints on how well the moon differentiated. They also hint at how much mixing occurred after early formation. A calm limit of observation enters. Composition inferred from surface brightness and spectra is not unique. Dust coating can mimic a different rock type. Space weathering darkens and reddens surfaces over time. Small grain sizes scatter light differently than large blocks. The limit is specific. Remote inference has degeneracy. Multiple compositions can produce similar signals. Only careful context and sample calibration narrow the options. Even with this limit, broad patterns persist. Highlands remain dominated by bright crustal material. Some basins and peaks reveal deeper components. Mare plains show basaltic fills. The transition between bright and dark is often a boundary in topography and thickness. The section moves toward consequence. Impacts do more than expose. They also create basins that later collect lava. Basin rings and fractures can guide melt upward. The next section moves from impact windows to volcanic flooding, where dark plains spread like cooled ink across low basins without erasing the older crust beneath. Dark plains spread across the moon like quiet floods that settle into the lowest places. The Maria form when basaltic lava fills impact basins, and the timing reveals how the moon cools from inside. In that region, the boundary between bright highlands and dark plains is sharp. It follows basin rims and low rings. The dark surface is smoother. It reflects light more evenly. The bright surface is rougher. It scatters light with a fine sparkle of small facets. The first small payoff arrives early. Dark does not mean young in every case, but smooth dark plains usually mean later resurfacing. The smoothness is the clue. The lava arrives after the basin exists. It ponds in the deepest floor. It spreads outward in thin sheets. The edge of each sheet can freeze into a low ridge. Ridgelines curve like contour marks on a map. They overlap and branch. The physical detail is clear. Flow fronts leave lobes. Lobes leave wrinkle ridges when cooling and contraction compress the surface. A unique visual anchor settles in. A mare plain lies under a low sun. Long ridges cast narrow shadows. Between ridges the ground is flat and dark. A few bright craters puncture the plain. Their ejecta rays form pale fans across the dark background. The rays fade as distance increases. Their edges are soft where dust settles. Light behaves as a gentle sheen on the mare. It looks almost velvety compared with the glitter of the highlands. The next payoff follows. Bright rays on dark plains act as a relative clock. The crater that produces them must be younger than the plain it crosses. One key term enters softly. Basalt means dark volcanic rock from low viscosity lava. The definition stays short. The image follows. It is like thin syrup that spreads before it cools. It matters because low viscosity allows lava to travel far and fill basins smoothly. A second concept holds the mechanism. Partial melting means only some of the mantle melts. The definition stays short. The image follows. It resembles butter softening in a warm pan while some parts remain firm. It matters because partial melting concentrates certain elements in the melt. Those elements influence density and flow. The first small payoff returns in a new way. Basaltic melt can rise more easily through fractures created by impacts. A basin is not only a hole, it is a network of cracks and weakened rock. Those weaknesses act as pathways. A calm analogy anchors the process. A sponge squeezed under a shallow bowl releases water toward the center. The bowl is the basin. The sponge is the warmed mantle. The water is melt that finds the easiest routes upward. The analogy stays gentle and does not claim perfect similarity. It simply keeps the direction clear. One number sets the timeline without strain. Many mare eruptions peak around 3.5 billion years ago, like a midpoint between the moon's birth and the quiet present. The comparison stays plain. 3.5 billion years is deep time. It signals that volcanism persists long after crust formation. The scale shift follows. A lava flow advances in hours or days. It cools on the surface in weeks. Its interior can stay warm for years. The overall episode spans thousands of years. The record then sits under slow dust gardening for billions of years. A second visual anchor arrives to keep the rhythm. A sinuous channel cuts across a mare. The channel is shallow and winding. Its banks are low. Along one bend, a collapsed roof leaves a chain of pits. The pits cast neat oval shadows. The payoff follows. Channels and pit chains suggest lava once moved beneath a crust. A roof can freeze on top while fluid still moves below. When the roof collapses, it reveals the path. This gives a quiet glimpse of flow style. Not all lava is a simple surface river. Some travels as covered tubes. The surface texture adds another clue. Parts of the mare show faint ripples. Parts are blocky with small plates. Ripples indicate smoother flow. Plates indicate cooling and breaking of a crust as it moves. These are small details. They are consistent with basaltic flooding. They help distinguish mare from impact melt sheets. A calm limit of observation enters. Composition inferred from darkness and smoothness is not unique. Dust thickness can alter brightness. Space weathering can darken old surfaces. Some impact melts can look smooth like lava. Without samples from every mare, uncertainty remains. Models of mantle melting must assume interior heat content and how it declines. Those assumptions are uncertain. The limit is specific. The exact volume of erupted lava over time cannot be measured directly. Only surface coverage and thickness estimates provide ranges. Even with this limit, the broader story remains stable. Mare eruptions are late compared with the oldest crust. They concentrate in low basins. They require an interior that stays warm enough for partial melting. That warmth can persist if the moon cools slowly beneath an insulating crust. It can also persist if certain elements concentrate and produce heat internally. The section draws back to a wide view. Dark Maria do not erase the moon's origin. They sit on top of older structure like a calm second layer. They reveal a moon that remains active for long spans. They also show how impacts and volcanism connect. Impacts create basins and fractures. Volcanism fills and smooths those basins. The next section moves from these surface clues to the long tidal link with Earth, where distance and rotation change together in steady, quiet steps. The Moon appears fixed in the sky, yet its orbit slowly expands like a quiet breath over eons. Tides exchange rotational energy and angular momentum, so Earth slows, while the Moon drifts outward. At this distance, the link begins as a simple shape in a fluid. A tidal bulge rises on Earth. It is a long oval swelling aligned roughly toward the Moon. The bulge has two peaks on opposite sides. The peaks are not perfectly aligned with the line between centers. Friction inside oceans and mantle drags the bulge slightly ahead of that line. The physical detail matters. The offset creates a torque. Torque is a twisting influence that changes rotation. The definition stays short. The image follows. It is like pushing on the side of a spinning wheel. The push does not stop the wheel at once. It shifts the wheel's timing. It matters because that gentle push transfers spin from Earth to the Moon's orbit. The first small payoff arrives early. The Moon recedes because Earth's tides act like a slow handoff of momentum. A steady visual anchor settles in. A dark ocean band circles an early Earth. The band is slightly higher where the bulge rises. On the far side, a second bulge mirrors it. Between bulges, the water level is lower. The boundary between high and low is a soft slope. Light behaves as a subtle sheen on the bulge crest. The sheen fades toward the trough. The whole pattern rotates with Earth. The Moon's gravity holds the pattern, yet friction distorts it. The next payoff follows. The tidal bulge is not only a surface wave, it is a lever arm that can nudge an orbit. Another concept enters gently. Tidal dissipation means tidal energy turns into heat through friction. The definition stays short. The image follows. It resembles kneading thick dough. Motion becomes warmth. It matters because dissipation is the reason change continues. Without dissipation, tides would rise and fall with no net transfer. With dissipation, the system evolves. One number anchors the present trend without strain. The Moon drifts outward by about 4 centimeters each year, like a fingernail growing over the span of seasons. The comparison stays ordinary and calm. 4 centimeters is tiny per year. Over billions of years, it becomes vast. The scale shift follows. In a single day, the Moon's position change is smaller than dust. In 1,000 years, it becomes the width of a field. In 1 billion years, it becomes a shift of many Earth radii. The ladder of time rises softly. Each rung shows how a small rate accumulates into a large outcome. A second visual anchor arrives to keep the rhythm. The Moon hangs above a dark Earth limb. A faint shadow line crosses the Moon's face. The line is the edge of night. It moves slowly as the Moon turns. The same face remains oriented toward Earth. This is synchronous rotation. The term can stay plain. The Moon rotates once per orbit. The payoff follows. Synchronous rotation is a natural resting state for tides. Tides inside the Moon remove spin differences until the same face remains forward. A unique analogy anchors the mechanism. 2 gears in thick oil gradually match pace. One gear slows, the other gains steady motion. The oil warms slightly. The gears do not choose. The coupling does the work. Earth and Moon are not gears. The analogy only captures the idea of coupling and damping. It keeps the direction clear without adding noise. The section deepens with another physical detail. The tidal bulge migrates across Earth's surface as continents and ocean basins change. The pattern is not identical through time. Shorelines and basin shapes affect friction. A thicker ocean can dissipate differently than a shallow sea. A more rigid mantle can dissipate differently than a warmer one. The third payoff arrives. The recession rate is not constant through all history. It can speed up or slow down as Earth's interior and oceans change. This explains why a simple back calculation can fail. It also shows why tides connect geology to orbital dynamics. A calm limit of observation enters. Past tidal dissipation cannot be measured directly. It is inferred from models and from ancient rock records of day length. Those records are incomplete. They can be altered by later processes. Models must assume ocean depth basin geometry and mantle viscosity in the past. These are uncertain. The limit is specific. The system's history is under-constrained. Many dissipation histories can match the present recession rate. Even with this limit, broad conclusions hold. Tides transfer momentum outward. Earth's rotation slows over time. The Moon's distance increases over time. The Moon's early orbit likely begins much closer than today. A closer Moon means stronger tides. Stronger tides mean faster early evolution. The section returns to gentle imagery. A closer Moon makes a wider bulge. The bulge's crest is higher. The gradient into the trough is steeper. The ocean's motion is stronger. Heat from dissipation warms coastal seas. The warming is modest compared with the planet's internal heat then. Still, it is a real energy pathway. Over time, the bulge lowers as distance grows. The gradient softens, the torque weakens, the evolution slows, the closing turns toward consequence. The Earth-Moon system becomes a stabilizing pair through this long exchange. The next section moves from tides and distance to the varied impact outcomes that can create different disks, and why the giant impact family still leads to one consistent chemical outcome. The giant impact is one event in concept, yet it can unfold in many shapes when angle and speed change. Different impact geometries can still lead to one moon, when a hot disk mixes and then condenses. In that region, the first clue is the disk's form. A head-on collision makes a thick, compact cloud. A glancing collision makes a wider, thinner sheet. The sheet has an inner boundary shaped by tides. It has an outer edge where clumps survive. Between spiral lanes appear as density waves. Their curved ridges show where matter bunches. Their gaps show where matter thins. The physical detail is clear. Thickness is not uniform. It has gradients. Those gradients steer where moonlets form. The first small payoff arrives early. A moon does not require a single exact impact. It requires a disk that stays hot enough to exchange material and long-lived enough to assemble. 2 or 3 concepts hold the section. One is impact angle, the geometry of the collision path. It changes how much material is launched into orbit. Another is mixing, the process of blending vapor and melt between Earth and disk. Mixing is not perfect, yet it can be strong during a hot phase. The third is condensation, when vapor cools into droplets and solids. Condensation sets when chemistry becomes locked into minerals. Each concept stays light. Angle shapes the initial spray. Mixing shapes the chemical similarity. Condensation shapes the final record. A unique analogy anchors the variety. A brushstroke across wet paint can be thin or thick depending on pressure and direction. The colors beneath can smear together when paint stays wet. When it dries, the smear becomes fixed. The impact is not paint. The analogy only holds the idea of geometry and timing. It keeps the path calm and concrete. A slow visual anchor settles in. A crescent of molten debris arcs around Earth. The arc is brightest near the planet where vapor is dense. It fades outward into darker beads. The arc thickens in one quadrant where the collision launched more mass. In the opposite quadrant, the arc is thinner. The imbalance makes the arc wobble as it orbits. The wobble becomes a slow precession. The second payoff follows. Even an uneven disk can settle into a more symmetric ring because collisions and waves redistribute mass. Redistribution is the quiet work that turns a messy arc into a stable assembly zone. One number anchors scale without strain. The impactor can be roughly Mars-sized, like comparing a grapefruit to a larger melon in the same basket. The comparison stays plain and safe. Mars size means enough energy to melt. It means enough mass to launch a disk. It also means enough momentum to change Earth's spin. The scale shift follows. The collision lasts minutes. The disk evolves over years. The moon assembles over centuries to thousands of years. The orbit then evolves over billions of years by tides. Each rung widens the view without raising intensity. The section moves through a checkpoint. In some scenarios, much of the disk comes from the impactor. In others, more comes from Earth's mantle. If the disk were mostly foreign, isotopes could differ. If mixing is strong, isotopes can converge. The payoff arrives. The chemical similarity of Earth and Moon strongly favours either Earth-rich disks or intense post-impact mixing. This narrows the family of acceptable impacts. It does not demand one exact path. It demands one outcome. A second visual anchor arrives to keep the rhythm. Moonlets form in the outer disk. They orbit in a loose chain. Their shadows overlap across the disk like faint stains. As they collide, splashes of melt flare briefly. The flares cool into droplets that rejoin the chain. The chain gradually becomes fewer bodies. Fewer becomes one. The payoff follows. Merging can erase initial differences between moonlets. Each merger reheats material. Reheating allows further exchange with surrounding vapor. This pushes composition toward a shared mean. It also pushes volatiles toward escape. The section adds a gentle limit of intuition. It is tempting to imagine the impact as a clean billiard strike with one predictable result. Reality is not so tidy. Numerical models depend on assumptions about material strength and phase changes. They approximate how rock behaves when it is partly vapor and partly melt. They must choose how finely to track fragments. The limit is specific. Limited resolution blurs small-scale turbulence and droplet exchange. Different codes can produce different disk masses for similar inputs. Even so, robust features appear across many models. A disk forms for a wide range of angles. A tidal boundary exists. A mixing phase is likely when temperatures are high. A condensation sequence follows as heat radiates away. The section returns to concrete features that survive. Volatile depletion persists as a trend. Oxygen isotopes remain close between Earth and Moon. The Moon remains low in metal compared with Earth. These are the anchor points. They are not sensitive to every detail of the impact. They are sensitive to whether the disk is hot and Earth connected. The closing eases toward a wider view. The giant impact becomes less like a single picture and more like a family portrait with shared traits. The next section moves from this family of impacts to the quiet uncertainties that remain, and how limits of evidence shape what can be stated with confidence. Some of the strongest evidence is also the hardest to read because the earliest record is thin and often rewritten. Uncertainty remains because models and samples have limits, yet the main constraints still converge on a hot mixed disk. At this distance, the Moon's surface looks calm. It is quietly complex. Bright highlands show countless small pits. Dark plains show smoother sheets with wrinkle ridges. Between them lie boundary zones where ejecta blankets overlap lava. The overlaps create mottled textures. A ray streak can cross a mare and fade at the far rim. A crater can cut through a ray and reveal older dark material below. The physical detail matters. Overprinting is common. It hides first layers beneath later ones. The first small payoff arrives early. A messy surface can still preserve order if relationships are red. A feature that cuts another is younger. A blanket that lies on top is later. A boundary that is sharp can mark a change in material. A boundary that is diffuse can mark gradual mixing of debris. These are simple rules. They allow a relative story even when absolute dates are hard. A unique analogy anchors the limits. The early Moon resembles a long-used chalkboard. New writing appears on top. Some lines are wiped, some are smudged. The board keeps traces, yet not every lesson remains legible. The analogy stays gentle. It emphasizes partial preservation without implying total loss. A slow visual anchor settles in. A highland ridge runs toward a basin rim. Along the ridge, small craters pock the crest. Their rims are sharp. Their floors are dusted smooth. At the rim, terraces step down into the basin. Each step has its own shadow band. On the basin floor, a smooth melt sheet glints faintly. Across that sheet, faint ripples curve. The ripples are frozen flow lines from impact melt. They resemble lava, yet their context differs. The next payoff follows. Context matters more than appearance. A smooth surface can come from impact melt or from volcanic lava. The distinction comes from where it sits and what it covers. A concept enters softly. Degeneracy means different causes can produce similar signals. The definition stays short. The image follows. Two different keys can open a similar-looking lock if the lock is worn. It matters because brightness, smoothness, and even chemistry can sometimes be matched by different histories. This is a limit of inference, not a failure of logic. Another concept holds the modelling side. Resolution means the smallest detail a model can represent. The definition stays short. The image follows. A woven cloth looks smooth from far away. Up close, it is threads and gaps. It matters because disk simulations cannot follow every droplet and eddy. Small-scale turbulence and droplet exchange are averaged. Averaging can shift outcomes. It can change how much mass stays in orbit. It can change how thoroughly vapor mixes. The first small payoff returns in a new way. Even when fine details are uncertain, certain large-scale requirements remain. A moon-sized companion needs enough mass in orbit. Similar isotopes require either Earth-rich debris or strong mixing. Volatile depletion requires high temperature and some escape. These requirements are broad. They do not depend on any one tiny parameter. One number anchors the limit without strain. A typical simulation may track millions of particles, like trying to describe an ocean using only a handful of grains of sand. The comparison stays ordinary. Millions sounds large. It is still sparse compared with the real number of droplets. This sets a calm scale shift. A droplet exchange happens in moments. A global disk pattern evolves in weeks. A simulation step advances in small increments. A planetary history spans billions of years. The gap between scales is part of the challenge. A second visual anchor arrives to keep the rhythm. A thin ring of debris is shown from above. It has spiral arms that tighten and loosen. The arms are denser lanes. Between them a faint haze remains. Small clumps form in the outer lane. Some are stretched into arcs near the inner boundary. Others survive and merge farther out. The payoff follows. Many different starting impacts can still produce similar disk structures because tides and rotation impose common boundaries. Those boundaries shape where survival and growth occur. Uncertainty also comes from the samples. The Moon's rocks represent a subset of terrains. Some are crustal, some are basaltic. Few come from deep mantle. Many have been shocked and heated. Shock can reset mineral clocks. It can move elements along microcracks. it can alter isotopic ratios slightly. The limit is specific. Sample bias and shock alteration restrict what can be concluded about the entire Moon. Even oxygen isotope similarity, while strong, is measured in a limited suite. Another uncertainty lies in volatiles. The Moon is depleted overall, yet some pockets and minerals show water and other volatiles. These may come from later delivery or from retained interior sources. The distinction can be subtle. Volatile content depends on trapping in crystals and later loss. The third payoff arrives. A Moon that is broadly depleted can still retain small amounts in protected reservoirs. This does not break the hot disk picture. It refines the details of escape and retention. The section returns to the calm center. The evidence is not one perfect line. It is a bundle of constraints. Each constraint has error bars even when not spoken aloud, yet the bundle points in one direction. A hot impact produces a disk. A disk mixes material. A disk loses some volatiles. A disk assembles a Moon. The closing turns gentle. With limits acknowledged, the next section widens from uncertainty to consequence, showing how the Moon's origin reshapes Earth's interior and atmosphere without requiring any new mystery. A single collision can reset more than an orbit because it reheats Earth and reshapes what stays and what escapes. The Moon's origin explains changes in Earth's mantle, an early atmosphere through mixing vapor loss and long cooling. At this distance, Earth after impact is not a stable sphere. It is a glowing body with a skin that forms and breaks. Broad dark plates drift on a red surface. Between plates, seams open where hotter melt rises. The seams are narrow. They trace branching paths. Their edges glow brighter than the surrounding crust. Above the surface, a thin haze of rock vapor lingers. The haze is denser near the equator. It thins toward the poles into clearer space. The first small payoff arrives early. A hot Earth provides the mixing needed for Earth-like lunar chemistry, because the mantle is stirred and homogenized. 2 or 3 concepts hold the section. One is mantle mixing the blending of melted silicate rock in Earth's interior. The definition stays plain. It matters because it can erase earlier differences between regions of the mantle. Another is volatile loss, the escape of easily evaporated elements and compounds. The definition stays plain. It matters because it can change the planet's early atmosphere and surface reservoirs. The third is equilibration, the tendency for materials in contact to exchange and approach a shared composition. The definition stays short. The image follows. It resembles 2 warm pools connected by a narrow channel. Water levels and temperatures slowly even out. It matters because contact between Earth's vapor and the disk allows exchange. A unique analogy anchors the larger transformation. The impact resembles shaking a layered bottle of oil and water, then letting it settle. The layers mix. Tiny droplets form. Over time, separation returns. The bottle is not Earth. The analogy captures the sequence of mixing followed by relayering. It keeps the logic calm. A slow visual anchor settles in. Visual anchor. The night side of Earth shows a dim red arc. The day side is brighter where fresh melt is exposed. The boundary between them is a broad gradient. The gradient drifts as Earth rotates. Along the gradient, the vapor haze scatters light into a faint halo. The halo is thicker near the limb. It is thinner above cooler plate patches. The next payoff follows. A vapor halo can slow cooling by trapping heat, extending the time for exchange and mixing. This helps Earth and Moon share isotopic signatures. It also helps drive volatile loss by keeping temperatures high. One number anchors the scale without strain. The impact energy is enough to melt a large fraction of Earth's outer mantle, like turning a thick rind into a moving liquid shell around a fruit. The comparison stays simple and does not chase exact percentages. The point is volume. Volume means long cooling time and strong circulation. The scale shift follows. A seam opens in minutes. A convection cell turns in days. The magma ocean cools over tens of thousands to millions of years. The consequences then persist over billions of years in mantle structure. The time ladder rises smoothly. Each step is a softer change. Volatile loss becomes more concrete. In that hot phase, molecules and atoms at the surface enter vapor easily. Lighter species drift upward into space more readily. Heavier species can recondense and fall back. A boundary layer forms where exchange happens. It is thin. It sits above molten rock like a shimmering film. Across it, atoms move in both directions. The film has a gradient. Near the surface, vapor is richer. Higher up, vapor thins. The third payoff arrives. A boundary layer is enough to bias what remains. Over long cooling, repeated evaporation can reduce certain volatiles even if some returns. This supports a drier early Moon and a reshaped Earth atmosphere. The section ties the Moon to Earth's interior. If the disk draws from mantle-like material, then Earth's mantle loses a portion of its outer layer. That loss is small compared with Earth's mass. It can still matter for composition. It can change ratios of elements that prefer the crust. It can alter how heat-producing elements are distributed. The result is subtle. The payoff follows. The Moon's formation can act like a selective skim from Earth's outer silicate reservoir, leaving behind a mantle that is slightly modified and thoroughly stirred. A second visual anchor arrives to keep the rhythm. A glowing ring of debris circles Earth. Its inner edge is ragged where tides shear clumps. Its outer band is dotted with growing moonlets. Beneath the ring, Earth's surface shows darker plates riding on a brighter sea. Shadows from the ring fall faintly across the haze, creating a soft banded pattern. Light behaves as a diffuse glow through vapor. The scene links two systems without needing any machinery or observers. A calm limit of observation enters. The early Earth surface leaves almost no direct record. Plate tectonics and later impacts recycle crust. The mantle record is indirect. It is inferred from modern rocks and isotopes. Models of volatile escape must assume early solar conditions and atmospheric composition. Those assumptions are uncertain. The limit is specific. The exact inventory of lost volatiles cannot be reconstructed uniquely. Only bounds and trends are possible. Even within those bounds, the story holds. A hot post-impact Earth encourages mixing. A vapor phase encourages exchange with the disk. High temperature encourages volatile loss. Long cooling times allow these processes to act. The closing eases toward a wider consequence. The Earth-Moon pair becomes not only a dynamical system but a shared chemical history. The next section moves from these Earth-side consequences to long-term stability, showing how a large moon can steady tilt and influence climate rhythms without any sudden drama. A planet's tilt can wander like a slow wobble, yet a large companion can steady the motion over long spans. The moon helps stabilize Earth's axial tilt by adding gravitational torque that resists large chaotic swings. At this distance, the idea begins with a simple geometry. Earth spins with an axis that is not perfectly upright to its orbit. The axis traces a small circle in space over time. This tracing is precession. Precession means the spin axis slowly sweeps like a tilted top. The definition stays short. The image follows. A spinning top leans and its tip circles. The top stays spinning. The circle is smooth. It matters because Earth's tilt is not fixed. It shifts under gravitational pulls. The first small payoff arrives early. A steadying torque from the moon makes the tilt's motion more regular, so extreme swings become less likely. A unique visual anchor settles in. Earth is seen as a sphere with a faint polar cap shadow. A thin line marks the equator. The line is not bright. It is only a guide. The spin axis is suggested by a line that points slightly off perpendicular. Over many rotations, the axis tip traces a slow loop. The loop is subtle. It is like a small ring drawn in the darkness. Light behaves as a broad gradient across the planet. The gradient shifts with seasons. The loop remains slow and steady. 2 or 3 concepts hold the section. One is obliquity, the angle between spin axis and orbital plane. The definition stays short. The image follows. It resembles a slightly tilted lamp that casts longer shadows on one side of a room. It matters because obliquity shapes seasonal contrast. Another concept is torque, the twisting influence that changes orientation. Torque has already appeared. Here it acts on direction rather than speed. The third concept is resonance, when periodic motions can amplify each other. Resonance can be gentle or disruptive. The definition stays short. The image follows. A swing pumped at the right rhythm grows higher. It matters because Earth's tilt can be influenced by resonances with orbital cycles. The moon shifts Earth's precession rate. That shift can move Earth away from some resonant conditions. The next payoff follows. By changing the rhythm of precession, the moon can reduce the chance that small nudges line up into large changes. One number anchors the present tilt without strain. Earth's tilt is about 23 degrees, like leaning a plate slightly, so water would run to one edge. The comparison stays plain. 23 degrees is not steep. It is enough to produce seasons. The scale shift follows. A day sets the spin. A year sets the orbit. Thousands of years modulate precession. Millions of years modulate long-term tilt variations. The ladder rises softly. Each step is a longer beat in the same quiet system. A second visual anchor arrives to keep the rhythm. A shadow line slides across Earth's surface over a year. At one time the light reaches farther toward one pole. At another time it reaches farther toward the other. The boundary between light and dark is a curve. The curve's position changes with obliquity and season. Over long spans, the curve's extremes can shift. With the moon's influence, the extremes remain within a narrower band than they might otherwise. The payoff follows. A narrower band means less chance of extreme seasonal contrast driven by huge tilt swings. It does not freeze climate. It steadies a parameter that can otherwise wander widely in some scenarios. A unique analogy anchors the stabilizing effect. A slow gyroscope mounted with a weight on an arm resists being tipped quickly. The weight is the moon's gravitational pull. The arm is the Earth-Moon separation. The system is not a mechanical toy. The analogy captures the idea of added resistance to reorientation. It stays calm and does not claim exact equivalence. A calm limit of observation arrives. The long history of Earth's tilt is not directly recorded in a continuous line. Climate proxies are indirect and complex. They mix many influences. The early Earth has sparse preserved rocks. Models of spin-axis evolution require assumptions about interior structure and tidal dissipation. Those assumptions change through time. The limit is specific. Past precession rates and resonant crossings cannot be reconstructed uniquely. Multiple histories can fit partial constraints. Even with that limit, the present dynamics show a clear role. A larger companion increases the precession frequency. That shift changes which resonances are possible. It can make the system less sensitive to small perturbations from other bodies. The section returns to physical detail. The moon's orbit is inclined slightly. Its gravitational pull is not constant in direction. It varies through each orbit. The torque it exerts on Earth's equatorial bulge changes as well. The equatorial bulge is a subtle swelling created by rotation. The swelling provides a handle for torque. The handle is not visible as a shape from far away. It is real in the gravity field. The payoff follows. Without an equatorial bulge, torque would act differently. With it, precession becomes a stable response. This links rotation, shape, and orbit into one quiet system. A gentle consequence emerges. Stable obliquity supports more predictable seasonal cycles over long spans. Predictable does not mean unchanging. It means variations occur within a range rather than wandering wildly. The closing eases outward. The moon's origin thus echoes into Earth's long-term orientation. The next section widens again to the broader solar system where giant impacts shape many worlds, and where the Earth-Moon story becomes one example among many quiet collisions. A quiet collision can redirect the fate of a world, and the solar system holds many such silent redirects. Giant impacts are common in planet formation, so the Earth-Moon story fits a broader pattern of growth and reshaping. At this distance, the early solar system is a disk of dust and rock fragments around the Sun. The disk has dense lanes. It has thinner gaps. Within it, small bodies collide and merge. Some collisions are gentle. Some are energetic enough to melt surfaces and launch debris. The physical detail is clear. Each collision creates a spray with a gradient. Coarser fragments fall back quickly. Fine droplets and vapor can travel farther. The first small payoff arrives early. Giant impacts are not rare accidents. They are a natural outcome of crowded orbits where growing worlds cross paths. 2 or 3 concepts hold the section. One is accretion, the gradual growth by collisions and sticking. The definition stays short. The image follows. It resembles snow gathering into a rolling ball that picks up layers. It matters because planets reach their final size through repeated merges. Another concept is dynamical, stirring the process that excites eccentric and inclined orbits. The definition stays short. The image follows. It resembles a calm pond disturbed until ripples intersect and amplify. It matters because stirred orbits collide at higher speeds. Higher speeds increase melting and debris production. The third concept is debris disk formation, when impact ejecta remains in orbit and spreads into a ring. The definition stays plain. It matters because disks can produce moons and rings. A unique analogy anchors the broader view. A crowded dance floor slowly rearranges as pairs bump and separate, and occasional strong collisions change the whole pattern. The dancers are not people here. The analogy only captures crowding and chance encounters. It stays calm and does not add human scenes. A slow visual anchor settles in. A distant protoplanet is seen as a glowing arc on one side and a darker arc on the other. A smaller body approaches along a tilted path. The collision is shown without violence and sound. Material lifts into a crescent spray. The spray spreads into a thin ring with a brighter inner lane. The ring's outer edge breaks into clumps. The clumps trail faint shadows. Light behaves as a diffuse glow through vapor near the ring. The next payoff follows. The same physics that builds the moon can operate elsewhere. A disk forms when debris has enough angular momentum. A boundary forms where tides or gravity gradients prevent clumping. Condensation and cooling then decide what remains. One number anchors the timescale. The main phase of rocky planet formation lasts roughly 100 million years, like a long epoch compared with a human lifetime, but brief, compared with the age of the solar system. The comparison stays gentle and ordinary. 100 million years is enough for many collisions. It is also enough for orbits to evolve and cross. The scale shift follows. A single impact unfolds in minutes, a ring spreads in weeks, a moon assembles in centuries. A planet's final architecture emerges over tens of millions of years. The ladder widens without urgency. Different worlds show different outcomes. Some impacts strip atmospheres, some tilt axes, some create cores that mix or separate, some form moons, some leave rings that later disperse. The outcomes depend on angle, speed, and composition, yet patterns appear. Rocky bodies tend to differentiate. Their outer layers can be stripped and reshaped. Their volatile inventories can change. The second visual anchor arrives to keep the rhythm. A ring around a distant world is seen edge-on. It appears as a thin line with a brighter knot where clumps gather. The line has a slight warp. The warp shows that the disk is not perfectly flat. Over time, collisions within the disk damp the warp. The line straightens. The payoff follows. Collisions within a disk do not only build, they also smooth. They reduce random motion. They help a swarm settle into a plane. This is a quiet, self-organizing tendency. It supports the idea that a chaotic spray can become a coherent moon-forming environment. A calm limit of observation enters. Other giant impacts in the solar system's past are reconstructed from present properties. Those properties include density, spin, tilt, and satellite systems. Many different histories can lead to similar present states. The limit is specific. The initial conditions are lost. Only final outcomes remain. Even within simulations, small changes in input can yield different moons or none at all. Yet statistical reasoning helps. In a crowded disk, impacts of many scales are expected. In such a setting, a giant impact for Earth is not an extraordinary claim. It is a plausible step. The section returns to Earth and Moon as an example among many. Earth's large moon is not universal. It is a particular outcome that leaves clear chemical and dynamical traces. Those traces are strong precisely because the event is energetic and early. They include volatile depletion on the Moon, similar isotopes, and a long tidal evolution. The closing eases toward a soft landing. The next section gathers the story into a calm synthesis, holding the key evidence and consequences together, then letting the motion settle, without opening any new mysteries. The Moon hangs above Earth with a steady face, and its stillness is the end of many earlier motions. The simplest synthesis holds a giant impact, makes a hot disk mixing and cooling, then build a layered moon and a long tidal partnership. At this distance, the story begins again with one calm picture. A ring of molten debris circles a glowing Earth. The ring is not uniform. It has brighter lanes near the planet. It has darker beads farther out. It has an inner boundary where tides stretch clumps into threads. It has an outer band where clumps survive and merge. The first small payoff arrives early. A ring explains how a moon can form without capture and without co-formation in place. A disk is a natural assembly zone. It turns violent ejection into orderly orbit. A unique visual anchor settles in. The ring cools from red to dim grey. The glow retreats to the densest lanes. A chain of moonlets forms in the outer band. Their shadows overlap like soft stains on the disk. Over time, the chain becomes fewer bodies. Fewer becomes one. The surface of the growing moon turns from molten shine to a dull crust with faint cracks. The cracks form branching networks. Their edges catch low light. The second payoff follows. Repeated mergers reheat the forming moon. Reheating promotes mixing. Mixing supports the close isotope match between Earth and Moon. The same heat also encourages volatile loss, leaving the Moon generally depleted compared with Earth's mantle. 2 or 3 concepts hold the closing. One is mixing the tendency of vapor and melt to exchange and approach a shared composition. The definition stays plain. The image follows. It resembles warm ink spreading through water until the color evens out. It matters because it explains why oxygen isotopes are so similar. Another concept is differentiation, the separation into layers by density during cooling. The definition stays plain. The image follows. It resembles cream rising on cooling soup while heavier pieces settle. It matters because it explains a bright flotation crust and a denser interior. The third concept is tidal evolution, the slow exchange that moves the moon outward and slows Earth's spin. The definition stays short. The image follows. It resembles a gentle drag on a rotating wheel that transfers motion into a rolling path. It matters because it connects the early origin to the present orbit. One number anchors the full arc. About 4.5 billion years separate the hot ring from the quiet sky, like a long sequence of seasons that never repeats exactly. The comparison stays simple. It keeps deep time in view without making it heavy. The scale shift follows. A collision happens in minutes. A disk settles in years. A crust forms in millions of years. The orbit evolves over billions of years. The ladder widens and the tone remains soft. The moon's surface becomes a record of cooling and later change. Bright highlands form from floating minerals. Dark plains appear later when basalt floods low basins. Craters accumulate as a clock of exposure. Rays fade as dust churns. Each feature is a layer of time. The third payoff arrives. Many independent clues align. Similar isotopes point to shared source or strong mixing. Volatile depletion points to high temperature and some escape. A differentiated moon points to early melting and cooling. A long tidal history points to a close beginning and steady outward drift. Together, these clues support the giant impact framework without requiring perfect detail. A calm limit of observation is acknowledged without weakening the picture. The earliest disk cannot be sampled directly. The earliest Earth surface is not preserved. Models have finite resolution and uncertain material behavior at extreme temperatures. Sample collections represent limited regions. The limit is specific. Many different impact angles can fit the broad constraints and fine details of mixing rates remain uncertain. Yet the core requirements remain robust. A disk must form. A disk must cool. A moon must assemble. The Earth-Moon system must then evolve by tides. The closing returns to simple imagery. The moon's bright highlands hold gentle slopes. Their dust scatters light in a soft sheen. Dark maria sit in low basins. Their wrinkle ridges cast thin shadows. The boundary between bright and dark is often a rim line. It is a physical trace of topography and history. At this distance, Earth and Moon appear as a pair. One is active and layered. The other is quiet and cratered. Their shared origin is carried in chemistry, in structure and in motion. The final transition is gentle. The ring has vanished, the heat has cooled. The orbit continues its slow change. The story settles into a stable sky, and the remaining motion becomes a soft background rhythm.